And today we are here to see the talk by Professor Rajit Manohar from Yale University in USA. So the title, as you can see, is Asynchronous Logic, Design and EDA. So Professor Rajit is a professor of electrical engineering and computer science at Yale. He received his bachelor in 94, master in 95, and PhD 98 from Caltech. His group conducts research on the design, analysis, and implementation of self-timed systems. He is the recipient of 12 Best Papers Awards, 9 Teaching Awards, and was named to MIT Technology Review's top 35 young innovators under 35 for contributions to low-power microprocessor design. So this is just a short CV of a large set of achievements that are done by Professor Rajit. So thank you very much for accept our invitation. And the floor is with you to start your talk.
Thank you so much, and thank you for inviting me as well. Hi, everyone. I'm going to talk to you today about asynchronous logic, design, and EDA. So what I'll talk to, but this talk is sort of in two parts. The first part, I will talk to you about what's asynchronous design and some of the reasons people are pursuing asynchronous design for a number of different application spaces. And then I will talk about some of the challenges in trying to pursue asynchronous design, especially when trying to design large-scale systems, and some recent work we've completed that aims to address this challenge in the space of electronic design automation. So the word asynchronous design actually means a lot of different things to a lot of people. So I thought I would just clarify what I mean by asynchronous design before I proceed with my talk. If I think about computation as being divided into sort of 4 different buckets, there are 2 axes here. One of them is time, the space of the time, and the second axis is a value. So values in your computation could be discrete or continuous, so like a real number versus things like bits, zeros and ones, or multiple values as well. And similarly, time can also be discrete and continuous in your computation. And 3 of these 4 quadrants are very well understood and used and accepted. So discrete time, discrete valued systems, or digital synchronous logic is a classic example of computation like this. Discrete time, continuous valued system, a simple example is switched capacitor analog electronics, things like DC-DC converters, things like that use circuits like this all the time. Continuous time, continuous value is, a simple thing as a straight amplifier is something where inputs are viewed as continuous time, continuous value, and so is the output. But what I'm focusing on in this talk is a class of circuits that are continuous time, but discrete value. So time is continuous, but it's a digital computation from a value perspective. Now, when we design asynchronous circuits, so these are circuits where time is continuous, so you don't use a clock to discretize time. So time is continuous. And it turns out that a much easier way to think about how the computation is organized in chips that are implemented with asynchronous logic is to think of the chip as a parallel program. So you say there are lots of little circuits on the chip. They're all running simultaneously. And then they exchange information by, whenever they like, because it's continuous time. And they exchange information by sending sort of discrete values and messages. So in fact, actually, the most common hardware description language, the sort of highest level of abstraction for asynchronous logic looks much more like a software, message passing programming language. So that's a good mental model for how an asynchronous computation works. You have components. They send messages to each other, and then when you get a new message, that's new information, you can do some local calculations and then send the result as another message. There are 2 very standard ways. If you're worried about how you do this with signals and wires, there are 2 very standard ways to do this in an asynchronous computation. On the right-hand side of this figure, what I'm showing you, in this part of the figure, you have a sender sending a message to a receiver. So you have some number of wires that encode data. So these are just straight bits. And then the sender can tell the receiver with a request saying, here is a new piece of data. So you can say toggle the request to say there's new data. And then when the receiver accepts the value, it can toggle the acknowledge. And so that's sort of your classic handshake protocol. This is, ancient, right? This has been around since, well before I was born. But this is essentially an example of how you can do asynchronous communication. And then the handshakes are the ones that guarantee sequencing and reliable operation. Okay. The thing that is interesting in an asynchronous computation is this is continuous time. So you are allowed to change the request at any time as long as you obey the protocol for communication. And what that means is so if I send a request and the receiver accepts the data and does some complicated calculation, the time at which you might get the acknowledge can vary. It's not synchronized at a clock boundary or anything like that. It can change whenever it likes. So if I take a step back and just think about what's happening in my chip, let's say I have 3 parts of my chip doing 3 different calculations. And so I've shown this on the left-hand side, I'm showing you what it might look like in a synchronous computation. You have sort of 4 pieces of work, A1, A2, A3, A4. The part B, the B section of your chip is doing 4 pieces of work, and the C section of your chip is doing 4 pieces of work. Now, because A3 takes this certain amount of time, the y-axis is showing time, that sets the clock period, right? Because that's the slowest possible thing that your synchronous logic has to support. And so we discretize time with that clock period, and that's essentially how the computation proceeds. And so what you essentially have is these discrete points in time, and all this, you do calculations, and this is the next step, so you can use the previous step's result at this point. That's how it works. Now, in an asynchronous computation, time is viewed as a continuous value. So what happens is, again, I have these A1, A2, A3, A4, B1, B2, B3, B4, etc. But I have something else here. And what I'm showing with this something else are arrows. And those arrows correspond to information flow in the computation. So this arrow here says the result of C1 is used by B2. Right? So the point here is, as soon as you've sent this message over, you can start doing C2. But there will be some additional, potentially a little bit of overhead for doing this message passing. And so that's what that little purple barrier shows. And the real question is, when are you going to see? So you can see that you can start C1, C2 immediately after the message has been sent, and so on and so forth. Here, you were ready to start C3, but it needed the result from B2. So there was this little extra time gap here. So that's essentially the difference in how the computation proceeds. And so at the end of the day, you have to just ask yourself, I do the full computation, and which approach is going to give me a better result? And if it's the left, then a synchronous approach will be better. If it's the right, then an asynchronous approach will be better. Now, in case, people are usually very afraid when they think about trying to design complicated asynchronous circuits. In fact, most textbooks will include a little paragraph that says, don't do this. You're going to be in trouble. So I thought what I would show you is the fact that, asynchronous is nothing new, right? So this is my sort of cartoon timeline of various, at least according to me, at least very interesting milestones in history. And you notice I'm starting from 1940. And this first point here is the classic blueprint of the von Neumann machine. And if you read the section on arithmetic, they basically explain why you should do an asynchronous computation, because you can do much faster binary addition with a much cheaper circuit. Okay, so that's the pretty classic result. For those of you who are students of switching theory and history of switching theory, there is this classic 2-volume book by Miller in the mid-50s. And volume 1 is on synchronous design and volume 2 is on asynchronous design. They're given equal importance. And actually, if you look at some of the fastest machines in the world at the time, here I'm showing you a couple, the Iliac 2, the Atlas, they were all asynchronous machines. Okay, so that's very interesting. And then it turned out that there were certain technical difficulties in making large-scale asynchronous machines that they were not solved in the 60s. And so this approach was mostly abandoned. And then sort of people started getting interested again in asynchronous design in the late 1970s, early 1980s, because when the Mead and Conway classic VLSI book came out, it had an entire chapter called System Timing, written by Chuck Seitz, and talking about why asynchronous design was important. And so people started looking at this more seriously again, and there were a number of actually pretty important breakthroughs made in the 1980s that enabled the design in 1989 or 1988, depending on how you want to count it, of the first asynchronous microprocessor that was designed by my thesis advisors group at Caltech, by Martin. And after that, there have been a lot of other projects doing interesting results in asynchronous design, including a number of very famous neuromorphic chips like the TrueNorth chip or the Spinnaker chip or the NeuroGrid chip. There's a 10 gig Ethernet switch chip that was used for a while. It was an Intel product as well. It was done by a startup called Fulcrum Microsystems. That was the state-of-the-art switch chip that was available. Anyway, there were a number of different interesting results in asynchronous design that have said there's been a lot of activity in this space. So what I'd like to tell you next is sort of give you some intuition as to when asynchronous design might be a good idea. And I'm going to show you a number of different reasons why people do asynchronous design. And so the first most obvious one, and I already alluded to this in this particular example. So if you're looking at a computation and you look at how long it takes to produce a result, when you do an asynchronous computation, you just get the time that it takes for all the gates to switch and so on and so forth, rather than having to wait for potentially the slow path on your chip. And so the question is, how well do you do on average, right? Because you can imagine that the amount of time it takes to do some computation depends on the value of a data. So if I'm multiplying by 0, for example, that could be cheaper than actually doing a full-blown 64-bit multiplication. So you could build a circuit where multiplying by 0 is fast, so then you get a result quickly. That doesn't buy you anything in the clock design, but in an asynchronous implementation, it does buy you something. So the real question is, when is the average delay going to be better than the worst case delay on your chip? Okay, so there's a series of examples where people have looked at this particular issue, trying to exploit the gap between the average delay for computation and the maximum delay. And the classic, and this is the result I alluded to earlier in 1946 in the von Neumann machine, in the von Neumann blueprint for a general programmable machine. If I look at the problem of binary addition, we all know that the part that's slow in binary addition is the computing the carries, right? So here I've shown you the carries on the top. I'm adding two numbers, and then here's the result at the bottom if I didn't make any typing mistakes. So the interesting thing about carry calculations is it's when the inputs are different. So here you've got a 1, 0 and a 0, 1. So it's when the inputs are different that the carry out value depends on what the carry in was. But if it's a 1, 1, you know the carry out is 1 without waiting for the carry in. So in an asynchronous implementation, you can start the carry chain from any position in the adder where you've got a 1, 1 or a 0, 0, right? So then adder terminology, this is a generate or a kill. Now, if you assume that the location of these the input distribution is a uniform, identically distributed, independent, identically distributed random numbers, you can actually show that the average carry chain length for a ripple carry adder is actually log n steps, right? Even though it's obvious that the maximum delay is going to be order n steps, where n is the number of bits, right? And this was the argument used to say we should do asynchronous circuits. It's cheaper to do math. Now, well, you could look at that result and go, well, that's great, but I know how to build log n delay synchronous adder, so what? But it turns out that you can do actually something even more clever in the asynchronous implementation. So here is an adder topology where you have sort of a tree structure. You think of this as the carry chain calculation tree or a kill, propagate, generate tree. And you can do a standard adder tree and get log n latency. But what I can do is something very interesting in an asynchronous adder where I can, in addition to having the tree addition, I can have a ripple carry addition at every level of the tree. And at every location, I just take whichever result comes first. As simple as that. We know from a lot of theoretical results that the worst case delay for binary addition is not going to be better than log n, so you can't beat that. But what we showed was that in this particular topology, the average latency is actually not log n, but log n. And we can actually show that the latency for this is the best you can possibly do for any adder topology. You have a theoretical result that proves this. So this is very interesting because getting to below, so this is addition is a sort of a venerable old problem, I would say. And as recently as the 90s, we managed to find an improved adder topology that actually reduces not the worst delay, obviously, but the average delay. So that's an example of where an asynchronous design might be useful, where you've got a design where there's a big gap between the average delay and the worst delay. Now, something else you can do that is sort of very interesting is, and this is another category of reasons people use asynchronous design, is you want to look at data-driven power management. So what do I mean by that? So this is an example of a paper from the 90s where what they did was they designed an asynchronous FIR filter. They were trying to do this to build a low power filter for, I think it was a hearing aid application originally. And then so what they did was they had this asynchronous filter, but it was embedded in a clocked environment where there was some fixed data rate that had to be supported. But the filter had variable delay, so sometimes it was fast, sometimes it was slow, it depended on the data. And so what they did was they put FIFOs on the inputs and outputs of this filter to monitor how fast the filter was currently running. And so you can imagine this, if the filter starts getting slow, this input FIFO is going to become bigger, get filled up. If the filter is running fast, then this input FIFO is sort of slow, will be empty. So by monitoring the state of this FIFO, they could slow down the filter dynamically by changing the voltage. So there was an internal control loop based on monitoring the state of the FIFO to change the VDD for just the asynchronous part of the logic to save power, dynamically based on data. There were a number of other clever tricks in this. So for example, they had an addition and multiplication where if the top half of the data path was all zeros, they just did not use the top. They broke the data path and broke it into two components, and the top half would be not used, and only the bottom half would be used for small operands. So that's another example of where you can use data. So here you can see an example where the switching activity and the voltage is dynamic based on the values of what you're computing with. As an extreme example of this, we actually designed a full CPU like this. Where you basically, the data path could dynamically select how much of it is needed based on the number of significant digits in the integer operands. And if you take profiles from, say, spec benchmarks, so this is from a long time ago, from 2001, so these were old spec benchmarks at the time. But on a 32-bit processor, it turned out that sort of the average bit width that you really needed, if you looked at operands and all the data flowing through the register file and every arithmetic unit in the data path, was roughly a third of the maximum bit width that the data path supported. And so even though there's implementation overhead to represent where the data path should be broken, overall there's such a big reduction in the amount of switching activity you need that overall this was an advantage. Now, this is a very interesting example because if you do this in a clocked implementation, the worst case will become worse. Okay, so this is one of the very interesting things that you will see in an asynchronous implementation, that sometimes it pays to make the worst case worse if you can use that to make the average case better. But this is actually one of the interesting asynchronous design questions, because what happens is, because of this sort of observation, you end up, the way you get a big advantage with an asynchronous computation is you actually do the computation in a different way than the way you would do it in the clocked implementation. And so you save things at a sort of a higher level of design. You save things in the microarchitecture. The third reason where people have used asynchronous design is exploiting what I'll call the elasticity of pipelines. So let me try to explain what I mean by that. So imagine you've got a clocked pipeline, as I've shown here. And here I'm doing some combinational logic that does function f followed by g followed by h. And now essentially when the clock advances, the data that was here sort of moves in here, the data that was here moves here, the data result moves here, et cetera, et cetera. So at every clock tick, this pipeline advances one step. Now, in an asynchronous computation, this is not the case because every component of the pipeline can tell the next component when it's done. And what that means is the fact that you have this flow control and these handshaking signals, you actually know at every pipeline stage, do I have any valid data or not? And as a result, the throughput of this pipeline is going to depend on sort of how many tokens are flowing through it. So if there's only one token flowing through it, there's going to have a certain throughput. If there are two tokens flowing through it, the throughput might double, et cetera, et cetera. So it just depends on the way the pipeline is used. So the circuits themselves support some peak throughput, but the realized throughput depends on how occupied the circuit is with data tokens. And this is a big difference, actually. And this difference can be used for in very interesting ways. In fact, this difference can be so useful that there are plenty of clock circuit implementations where, in addition to the data, you have things like ready valid signals, a flow control, stop go, ready stop signals, et cetera, to basically get the same flexibility in a clocked implementation. Okay. But in general, the asynchronous pipelines are elastic. And I'm going to show you two examples of where this elasticity was exploited. Now, this was a paper from IBM, it's in 2002. This was actually eventually ended up shipping in some products for disk drives. Here there was an asynchronous FIR filter. Now, the core pipeline here is asynchronous, and there's a latency from input to output. That latency is some amount of nanoseconds or picoseconds, depending on how you like, what units you prefer, right? There's a fixed time budget for the computation. But this was a very interesting example because it was a FIR filter where they were looking at old spinning disk drives. And depending on where you were reading on the platter, in a fixed amount of time, you would get a variable amount of data. Okay? But this decoder had a fixed latency. So they ended up building this sort of synchronous environment with a variable number of clock cycles, a fixed latency circuit. And so one asynchronous circuit was supporting all the different frequency ranges that they needed. And then they just used control logic around it so that the synchronous environment knew exactly on which clock cycle they were going to get the next data value. So this is sort of a non-standard example, which is why I always like to use it. Here is another example where we used this elasticity to improve the performance of pipeline feed programmable gate arrays. So we built an asynchronous FPGA where we decided to add circuit level pipelining to the interconnect. So normally in an FPGA, the interconnect is not pipelined, and that's where all your delay is going. And this was a long time ago, so now almost 20 years ago, we designed this FPGA where we put asynchronous pipeline stages in the interconnect. And because they're asynchronous pipeline stages, it turns out that the place and route problem remains unchanged. So because adding a pipeline stage in a clock circuit might completely change timing, but adding an asynchronous pipeline because there's data tells you when it's ready, it doesn't change the computation. And so we were able to support a pipeline interconnects where if the place and route did a good job, we get run at very high frequency, but if they don't, then at least the circuit still works. So that's another interesting example where you can exploit pipeline elasticity. The next use case is timing robustness, taking advantage of timing robustness, and that's just because if the circuits have you have inherent built-in circuits that tell you when the result is ready. Then when the circuit delays change, you can design those control circuits to track that change. And so you can build circuits that are highly robust to variations in voltage, process, and temperature. This was an FPGA test setup where we tested the same chip running at things like liquid nitrogen. We used liquid helium and went all the way down to 12 Kelvin. You heated the chip up, and we also ran at room temperature, but we swapped the voltage as well while the chip was running. And the thing that's interesting is all of these experiments could be done while the chip was continuously running. We continuously vary voltage, temperature. The frequency, the throughput of the chip just changed, but other than that, there was no other issue. I'll skip this one. The next use case is when building sort of mixed signal systems. And here, when you're integrating analog and digital electronics, if you have an asynchronous system, it turns out that the time occurrence of switching activity is going to be distributed in time. It's not going to be aligned with the clock edge like it would be in a clock circuit. And as a result, if you look at sort of the frequency domain spectrum of the chip, it's sort of much quieter in terms of EMI and in terms of noise injection into the substrate. And this was used by Philips Research. This was one of their papers. This is a plot from one of their papers to look at the time and frequency domain of current and power and EMI emissions to show that, in fact, actually an asynchronous circuit helps them meet their requirements in a much easier fashion. And the last example I'm going to show you about another very interesting use case of asynchronous circuits is in doing continuous time signal processing. This is what I'm showing you here is a paper by Yanis Savidis' group. The idea here is instead of sampling an analog waveform using Nyquist sampling, instead what you do use a different sampling technique called level crossing sampling. So instead of sampling in time, you sample in value. And so what you do is you pick some number of levels, and when the signal crosses a threshold, so you get a sample, say at this point in time, you get another sample at this point in time, et cetera, et cetera. So you get all these different samples at different points in time. But essentially, if the signal is busy, you will get a lot of samples. And if the signal is quiet, you don't get many samples. And what you can prove essentially is that you can show this mathematically, that in a window of time, the amount of samples, you get enough samples so that you would reconstruct the signal. So you can show that you get samples that's roughly proportional to the local Nyquist rate. So, but the local, not the global Nyquist rate, and that's the big difference. So if you've got certain points when the signal's busy, but then a lot of times it's quiet, then you get bandwidth adaptive sampling sort of naturally with this kind of system. And we've also done some work in the space. We've designed ADCs and FIR and IIR filters that work on this principle. One other very interesting point that Yanis Savidis always likes to make is that you don't get any aliasing from sampling because you're not sampling the input. So you lose that particular source of noise. So I hope I've shown you a number of different interesting use cases where folks are interested in asynchronous design and why you might get advantages. And so maybe you've sort of decided that, hey, okay, this is interesting. I might want to consider designing an asynchronous chip. And so the question is, how do you sort of go about doing this? Well, if I was designing a clocked chip, I understand what I have to do. I'm going to write my design in some sort of RTL, in Verilog or VHDL or whatever your favorite hardware description language may happen to be this year. And then there are various commercial tools. You can use Cadence and Synopsys and I guess Siemens now, Mentor Graphics, or some combination of those tools to use ASIC flows and tape out your chip. You can verify things before tape out. It's all well understood. But now I'm trying to design an asynchronous chip. So how are we going to do this? Now, so I'm going to switch gears now to talk a little bit about EDA, right? And it's actually a major stumbling block. And I would argue, especially today, this is one of the biggest reasons why it's difficult for people to try to adopt this design methodology, is that there's basically very little EDA support. So I'll tell you what, I'll take a snapshot in time. So we've been working on a project, which I'm going to talk to you about next, on developing EDA support for asynchronous circuits. But when we started this project, we've had in-house EDA tools that we use in a variety of different ways, but nothing very robust or comprehensive like a commercial EDA flow. And the status as of 2018 is essentially different groups doing asynchronous design had sort of in-house sort of boutique tools or scripts that were good for small circuits. They could only do some part of the flow. But most of the time, every group had the asynchronous circuit family they were using, and that's it. They had local boutique tools that helped them design some small-scale circuits like that, but that was roughly it. And a few groups had in-house tools for custom design of large asynchronous circuits. And some of these groups are in industry, some of them were at startups. We had some of these tools in-house, but there weren't very many. In fact, I sort of know all the people. It's such a small community. But as soon as you try to do anything non-trivial, essentially everybody wanted to use commercial tools as much as possible. But there were a number of issues with using commercial tools. For example, you really can't use commercial logic synthesis because the commercial logic synthesis tools won't understand, for example, that a request and acknowledge signal have to be glitch-free. So how do we do that? How do we even express the fact that I'm doing the send and there's this timing constraint? All of these things were very complicated. And in particular, timing was quite inaccurate. That impacts all the tools. And asynchronous circuits have all sorts of state holding gates that are not just flip-flops and latches. This is, again, difficult for standard tools to handle. And what about SRAM, right? How do you do that? So there were a number of issues. And before I sort of talk about what we ended up doing, I will try to convince you that this was actually a non-trivial problem, okay? And the reason it's a non-trivial problem is there are a very large number of actually useful design points in the asynchronous circuit space. Now, if you think this is an issue with just asynchronous design, that's actually not true. There are tons of synchronous design logic families also. In fact, if you open a textbook on VLSI, you will see dozens of different types of latches, for example, different clocking strategies, all sorts of sophisticated approaches. But pretty much everyone uses commercial tools which have a certain style that they support well, and essentially the community has sort of converged to using those for large-scale system design, right? Now, in the asynchronous case, there are multiple of these interesting design points that are useful large-scale design points, depending on what you're trying to achieve. If you were trying to design a circuit that was incredibly robust to, say, process voltage temperature, you would pick a particular circuit family. If you wanted the smallest area, you would pick a different circuit family. If you wanted to run as fast as possible, there's a third circuit family. Actually, there are too many. So the circuit size are different. And they all differ in what they assume about timing and delay and so on and so forth. And this is sort of my summary of some of the commonly used circuit families in the asynchronous circuit design literature. So how do we go about dealing with this issue? So actually, let me skip this. So what we did was we basically took a sort of a clean slate approach, and we said we are going to design a unified asynchronous design flow. We have a hardware description language that we developed called ACT, which stands for Asynchronous Circuit Toolkit. Somebody pointed out to me recently that it could also stand for Asynchronous CAD tools, which I think is a happy coincidence. There's a documentation online. It's open source. We posted it on GitHub. And the goal of this tool flow is to be neutral, that we support anyone's asynchronous circuit family. And I believe we have actually accomplished this, and I will talk to you a little bit about how we did it. So remember I said an asynchronous design is best thought of as a collection of components communicating by sending messages to each other. That's at the behavioral level, that's the most convenient way to think about the computation. So in ACT, in the design description, we actually have a message passing programming language as the behavioral abstraction. So you can say send and receive. I'll show you a very simple example of what this looks like. And at this level of abstraction, I don't have to say what protocol I'm using for communication. Am I doing request acknowledge? By the way, I use it in my class on asynchronous design. I can spend a couple of weeks talking about all the different options for communication, but you don't have to pick them in ACT when you say I'm doing message passing programming. We also support data flow. So it turns out that data-driven computation very naturally ties into asynchronous circuits. And there are some circuit families where they only know how to build the circuits for data flow components. So to support those, we can also express your computation directly in data flow. Then there is a signal transition level. So you have Boolean wires. I say, this goes up, this goes down, and what order in which they happen, called handshaking expansions. And finally, you can just write gates. If you like pull up and pull down networks, you can actually directly write those in ACT. You can even specify transistor sizing, whether you want low VT transistors, whatever level of, you can basically do circuit design in this language as well, if you like. But what's actually very interesting about ACT is that you can mix and match approaches. So you can have part of your chip at the behavioral level and part of the chip at the gate level. And ACT understands that, and the communication between those two is automatically handled by the infrastructure. So you will have to tell me that the channel that you're going to use to talk to, you have to tell me what protocol you want to use and so on and so forth for the channel, and then it'll convert it into an interface that can talk to gates. So all of this is done automatically for you. You don't have to manually do any of these things. We also support sort of black box components for integration of third-party IP. So that also works. Just to show you what this looks like, I'll pick the example on the right-hand side because it's easier to read. By the way, the CHP notation that I have on the left, this has been used in the asynchronous community starting from the early to mid 1980s. So this is a very old language. Okay, so if the syntax might look unusual to you, but in the asynchronous community, this is actually very old. So this says I have a component. This would be a module in Verilog, if you like. There's a process. It's an incrementing buffer. It has an input. This question mark means input. It has an input channel that takes integers called L. So think of it as an L input here, an R output here. I declare a local variable X, and then here is what this component does. It repeats forever. It does a receive into X, and then it sends X plus 1 on R. So that's a very simple component, and that's going to be asynchronous. It gets an input. It takes whatever value it receives, it adds 1 to it, and sends it on the output, right? So that's an example of how you would do behavioral description in ACT. Once you've got the behavioral description of your entire design, we have a simulator for you, so you don't have to figure out what to do with this. We have a simulator that understands this language, and it even supports analog simulation in SPICE. At the SPICE level of abstraction, we use the open source Zeiss simulator from Sandia National Labs. So we can support a design that is at the CHP level, at the signal level, at the gate level, as well as the analog level, and do a mixed mode simulation without the Axim can handle that all automatically for you. It has a lot of useful features. We've used Axim to design pretty large and pretty complicated chips. We can save VCD files. You can view waveforms. But from an asynchronous design perspective, what's incredibly helpful is Axim will tell you if you've got asynchronous timing constraint violations. It'll tell you if there are glitches on signals that shouldn't have glitches. It auto detects all of these things for you. So from an asynchronous design perspective, it's very helpful for functional verification. Now, the last sort of main thing I want to talk to you about is how we support different circuit families. Remember, I said one of the key things in our framework is we would like to support a large family of asynchronous circuits. And the question is, how do we do this? And it turns out that this is actually this is hot off the press, this particular paper. So the key primitive that we support in ACT to talk about timing constraints is something we call a timing fork. So a timing fork is, here in the bottom, I'm showing you an example of what a timing fork looks like. So this is actually from a particular paper, doesn't really matter. But the idea is I've got some set of gates here, some sequence of signal transitions here, and another set of gates here. And the assumption here says that starting from this point, this green path must be faster than this red path. That's the timing constraint. And so sort of in a more abstract way, you've got some gate. At some point in time, it changes its output, and that goes to one path and a different path. And we need to know that the range of delays from A to B versus A to C, the two endpoints are completely ordered in time. That's what we call a timing fork. And what we recently showed is this primitive is universal. All timing constraints for ordering events in any circuit family can be expressed as timing forks. This includes setup and hold time in synchronous logic as well. And to support timing forks, we've actually developed our own static timing analysis engine that can analyze the performance of your asynchronous circuit, but it can also compute timing fork margins. So it'll tell you if you've got violations of timing forks. We can show you top K violations, all those sorts of things. So we've got our own timing analysis and STA engine. I'm not going to get into how we do timing analysis, but the important thing I want to point out here is in an asynchronous circuit, the timing analysis problem is much more complicated because you actually have to analyze cycles of gates. In a normal synchronous circuit, if you gave it something like this, if you give the synchronous STA engine something like this, it'll complain saying there's a combinational loop. But we can actually analyze these in the asynchronous STA engine. I'm not going to get into how we do that. We've developed our own placement engine. So we support what are called gridded cells. so that we can have cells that have multiple, can have cell widths that are an integer multiple of the routing track, but also cell heights. It turns out that this really helps in that asynchronous, for some asynchronous circuit families, because they have a lot of very small gates, and they would become bloated, become much bigger, and have a much bigger area penalty than you might otherwise expect if you used just standard cells. And to support this, we have our own sort of global placement, detailed placement, and legalization approach that can handle gridded cells as well. And in our experience for asynchronous designs, we find that this saves between 10 and 20% of area for the exact same transistor netlist, right? So the LVS will match. The transistor by transistor, we can match both placements, gridded, non-gridded, and you'll see an advantage. We also developed a memory compiler to support asynchronous design. We have an internal version that actually works through all the design rules up to 12 nanometer. So we've got, we've taped out test chips with this memory compiler as well that are working. And finally, just to show you, we've got large pieces of the flow. We start from our design. We can do tech mapping. We also have exports to industry standard formats like Verilog, Spice, and LeftDef. We take SPEF and we generate. We can also take .lib files for timing, and then we've got our own place and route flow. And we stop at global routing because the detailed routing and layout finishing problem is not that different for asynchronous versus synchronous logic. So for that, we reuse the synchronous tools. So we rebuilt all the things that are asynchronous specific and where asynchronous timing makes a big difference. Finally, just to show you that we actually build chips on a regular basis. We've taped out many chips with this flow. We've done memory validation chips. We've done we've used these chips, these tools to teach classes. I teach my VLSI class with these tools. Students have been using these tools since 2019 and have successfully taped out chips with them. And there I know for a fact that there are at least two pretty major semiconductor companies that are in fact using our tools internally, at least to see how well they work and whether they might want to use them for production in part of their production flow for some different applications. So with that, I will try to stop. Just to summarize, I sort of gave you sort of 6 big reasons why people look at asynchronous logic. To support people who are interested in designing asynchronous logic, but who may not be sort of experts in that, we've developed a new open source EDA flow. It's available on GitHub. Various pieces are available on GitHub. A big chunk of it is available on GitHub right now. Any piece that's not available on GitHub is basically because there's a pending publication. Once the paper is published, then we make the tools available on GitHub. That's sort of the protocol we've been following. I've summarized a pretty large body of work here. A lot of the work was done by many of my students contributed to this work, and we had a lot of long-term collaborators. So I would like to thank all of those folks. I want to acknowledge them. These are some of the former students, postdocs in my group that developed the EDA flow. For example, Samira developed the memory compiler, cell generation, Ruslan, timing analysis, Wenmian, and a few other people. Many of the design examples I showed you were also done by students in my group. Some of them were done by other groups as well. But here are some of my students who developed a lot of the design. And 3 long-term collaborators, Professor Keshav Pingali from UT Austin worked with us on the EDA flow, Professor Kwabena Bohan at Stanford, and Professor Dharmendra Mode at IBM, Dr. Mode at IBM. We worked together on neural architectures and continuous time asynchronous logic, and all the folks at funding agencies that actually pay the bills. We'd like to thank them for their support. So with that, I will stop, and I will be very happy to take questions.
So thank you very much. Very nice talk. Very nice work. So for all that are attending in real time the talk, please, it's time for the questions. So do your question as soon as possible in the chat channel, and then I will read them to Rajit. While waiting for other questions, so I have one. problem nowadays for critical application is that we have the effects of radiation in chips in the ground level. So how are the asynchronous circuits tolerant to this radiation comparing to traditional ones?
It's an excellent question. So the answer is like with many things in circuits, it depends. We've actually built circuit families that are completely radiation, well, not completely, but are radiation, very, very radiation immune. In fact, we built a fully rad hard FPGA where in the US, at least NASA has a test facility and they couldn't figure out how to make the chip fail. So that was pretty cool. So there are methodologies to take parts of asynchronous circuits and make them rad hard. So let me give you the quick answer to this. So there is for every gate in an asynchronous circuit, and this is the same as in synchronous. So if you do timing analysis, right, then you know sort of the window of vulnerability for the gate where a bit flip on one of the inputs can trigger an erroneous propagation, right? So which won't get masked. A bit flip doesn't get masked. So you can actually determine when that is and figure out what your failure rate is going to be, and then decide which ones you need to add additional logic to compensate for. So that's essentially the way it works. You can decide to make it fully robust. That has a price. It's a pretty big price, right? So if you want to make everything fully robust, the price is roughly 2.2x in area, right? As you can imagine, you roughly have to have a replica of everything to know what the right answer is for radiation. But there are other sort of, much less costly approaches where you only mitigate this, for example, on the state holding elements, not the combinational part of the design, things like that. So you can pull all the same tricks as well in the asynchronous case. But the analysis is more complicated. In fact, one little tidbit, because we did this work a long time ago on radiation immune asynchronous logic, our logic simulator, actually, you can model SEUs in it as well. Yeah. So you can see how well or not well it works.
Yeah, one interesting technique to cope with radiation effect is time redundancy.
Yes.
How you can apply this to the asynchronous?
Yeah, so you can do the same thing, it turns out. So you basically would have something where you repeat the computation in the same circuit and check. So you can do that as well. You can build that as sort of a higher level state machine. The one thing you have to be careful about is if the big thing you have to be careful about is if the radiation bit flip takes you into a state from which you can't escape, right? I mean, this is the standard problem. So that's the main thing you have to correct for. And if you take that into account, then you can apply this other technique. You can repeat as well. You can do time multiplexing as well.
Okay, we have here a question by Francisco Badenas from Federal University of Ouro Preto. Francisco Badenas is with University in Buenos Aires, Argentina. So do you think your async open source flow and design methodology could interface with the expansion of RISC-V, as is another major open source topic?
Yeah, absolutely. In fact, one of my PhD students has currently developed a RISC-V implementation using our tools, which is fully asynchronous. In fact, we even have, I didn't talk about this, but one of the tools that we have in our framework is an FPGA prototyping tool. So you will get a clocked simulation model for a commercial FPGA. So we've done that. Actually, he's booting an operating system on FPGAs on our asynchronous RISC-V model. So yeah, absolutely. There's no problem at all. The functional specification. So, RISC-V is an instruction set architecture. You can implement that with any circuit style you like. So yes, no problem.
Okay, thank you. So I have another question by Marcos Sartori, that is in Porto Alegre. What is the expected area power overhead of a circuit design with an ACT compared to an equivalent synchronous circuit?
Now this is a complicated question because I don't even, so there are different ways you can interpret this. So, essentially, we are designing asynchronous circuits because we are actually getting better area or better power or better performance than what we see as the commercial numbers in synchronous logic, right? So, and we can do that with ACT today. So, but the way we do that is we have a different design, different microarchitecture. And that microarchitecture actually gives bad results in the synchronous logic. So, so the problem is it's very difficult to say what is an equivalent synchronous circuit, because, I'll just give you a very simple example. There are hundreds of open source RISC-V is a great lead-in. There are hundreds of open source RISC-V processors with performance and area that vary by orders of magnitude, all in synchronous logic. So, which one should I compare with? So I think it's a difficult general thing to ask. We know that we can design much better circuits for certain applications that are asynchronous. My favorite example for this is in the space of neuromorphic computing. We worked on the True North chip, for example, and we roughly saved an order of magnitude in power compared to the synchronous equivalent. We know that because there was a synchronous equivalent that was actually designed by another group. We didn't talk. There were two different design teams. But the synchronous equivalent that's complicated. So if I take my asynchronous circuit and emulate it with synchronous logic, I could do that. But then the synchronous folks are going to say, well, that's not fair. I could do a better synchronous design. All true, by the way. But if I did that, then actually it would be much higher power. You could probably implement the same performance, but the power would be significantly higher than the asynchronous one. I can go the other way, though. So if you give me a clocked implementation, we have automation tools that will give you an asynchronous implementation that is roughly the same energy delay area. Okay, you shouldn't expect it to be much better. After all, I'm taking your design and re-implementing exactly the same thing. I'm basically emulating the synchronous implementation, so I should emulate the performance as well as a result. I have a student who's actually working on a translator, which will actually seems to, well, it depends on data, but it'll outperform the synchronous emulation, but that's still a work in progress. So yeah, so the problem I think is really that it's not so easy to say what is the equivalent synchronous version. But this is a problem in synchronous logic also. If I have a particular synchronous implementation, somebody else could come up with a different implementation that's much better, that's also synchronous. So I think it's so I think that's the challenge. I don't have a simple answer would be, I have an AND gate and my AND gate is better than your AND gate. Then this life is very easy. But that's really not the case. We're using the same technology. So the comparison ends up having to be done at a system level. And then there are so many things that can be varied that I can't give you a number for that question, for example.
Okay, thank you. So new question by Bruno Sanchez from University of São Paulo. We would like to know if you can clarify how the async circuit can tolerate errors in the signaling flow of the async block in an environment with SUSET.
Oh, I see. Yeah. So, and you want the non-voting case. Okay. So you're constraining the problem so that you can't add any circuit correction, right? So, right. So if you look at if you have a sender and a receiver, now if I look at the receiver, depending on its state, there is a window of time when it will be observing the input. So if the SEU occurs in a window which is not observing the input, then you will ignore it. Essentially, you have the same effect as logic masking. So that is the only case where if you don't allow any circuit changes, this would be tolerated. Does that make sense?
Okay.
So the equivalent problem in clock logic is if you have a SEU on the gated clock, for example, it's the same problem. Which is why a lot of the space chips don't gate their clocks, actually. And they pay the power instead, pay for the power.
Okay, so thank you very much. I'm seeing no more questions in the YouTube channel. And so it was a very nice talk, very nice work. Thank you again for accepting our invitation.